Section 11.6, Phase Diagrams. The equilibrium between a liquid and its vapor is not the only dynamic equilibrium that can exist between states of matter. Under appropriate conditions of temperature and pressure, a solid can be in equilibrium with its liquid state or even with its vapor state. A phase diagram is a graphic way to summarize the conditions under which equilibrium exists between the different states of matter. Such a diagram also allows us to predict the phase of a substance that is stable at any given temperature and pressure. The general form of a phase diagram for a substance that can exist in any one of three phases of matter is shown in Figure 11.26. The diagram is a two-dimensional graph with pressure and temperature as the axes. It contains three important curves, each of which represents the conditions of temperature and pressure at which the various phases can coexist in equilibrium. The only substance present in the equilibrium is the one whose phase diagram is under consideration. The pressure shown in the diagram is either the pressure applied to the system or the pressure generated by the substance itself. The curves may be described as follows. Number 1. The line from T to C is the vapor pressure curve of the liquid. It represents the equilibrium between the liquid and gas phases. The point on the curve where the vapor pressure is 1 atmosphere is the normal boiling point of the substances. The vapor pressure curve ends at the critical point, which is the critical temperature and critical pressure of the substance. Beyond the critical point, the liquid and gas phases become inextinguishable from each other, and the state of the substance is called a supercritical fluid. 2. The line that separates the solid phase from the gas phase represents the change in the vapor pressure of the solid as it sublimes at different temperatures. 3. The line that separates the solid phase from the liquid phase corresponds to the change in melting point at the solid with increasing pressure. This line usually slopes slightly to the right as pressure increases because for most substances the solid form is denser than the liquid form. An increase in pressure usually favors the more compact solid phase, thus higher temperatures are required to melt the solid at higher pressures. The melting point of a substance is identical to its freezing point. The two only differ in the direction from which the phase is approached. The melting point of 1 atmosphere is the normal melting point. The point T, where the three curves intersect, is known as the triple point. All three phases are in equilibrium at this temperature and pressure. Any other point on the three curves represents equilibrium between two phases. Any point on the diagram that does not fall on a line corresponds to conditions under which only one phase is present. The gas phase, for example, is stable at low temperatures and low pressures and high temperatures, whereas the solid phase is stable at low temperatures and high pressures. Liquids are stable in the region between the other two. The phase diagrams of water and carbon dioxide. Figure 11.27 shows the phase diagrams of water and carbon dioxide. The solid-liquid equilibrium, melting point line of the carbon dioxide follows the typical behavior, slanting to the right with increasing pressure, telling you that its melting point increases with the increasing pressure. In contrast, the melting point line of the water is atypical, slanting to the left with increasing pressure, indicating that for water, the melting point decreases with increasing pressure. As seen in Figure 11.11, water is among the very few substances whose liquid forms are more compact than its solid forms. The triple point of water is much lower pressure than that of carbon dioxide. For carbon dioxide to exist as a liquid, the pressure must exceed 5.11 atmospheres. Consequently, solid carbon dioxide does not melt, but sublimes when heated at 1 atmosphere. Thus, carbon dioxide does not have a normal boiling melting point. Instead, it has a normal sublimation point. Because carbon dioxide sublimes rather than melts, it absorbs energy at ordinary pressures. Solid carbon dioxide, which is called dry ice, is a convenient coolant. For water to sublime, however, its vapor pressure must be below 0.006 atmospheres. Food is freeze-dried by placing frozen food in a low-pressure chamber below 0.006 atmospheres so that the ice in it sublimes.